como dos veces. Depende. Sí.
Ok, buenas tardes. Bienvenidos a una nueva sesión del seminario de DP en 15.000. Y hoy tenemos el gran placer de tener a la profe Hanne Bosch, que nos va a hablar sobre Spectrum of the Linearized Vlasov-Poisson equation. Adelante.
Muchas gracias. ¿Inglés o español?
No.
No. No, I will talk in English. So I will talk about the spectrum of the Vlasov-Poisson equation. So this is a model to study a large amount of particles or dust that are subject to their self-generated gravitational by their self-generated gravitational field. So if you have a large, okay, so we think about a large number of points, and each point, the microscopic description would be to have each point at some position xy and with some momentum py. And then you have a lot of points, and they move according to Newton's laws with a force that would be like the sum of 1 over the potential would be at x would be the sum of, for the particle I, would be the sum of the gravitational field. ¿Esto está aprendido? ¿Hay que aprender eso? Okay, yeah, okay. So this is the potential, and this is a sum over all different particles that are attracting one particle that is moving. And this becomes very complicated if the number of particles becomes large. So a very common approximation is that instead of keeping track of all the particles, we look at a quantity that is a little bit more macroscopic. That is this F that gives like a density depending on time, position, and momentum. In the sense that at each time, if I want to know how many particles I have in a box in phase space, so phase space it refers to that you look at positions and momenta, then you integrate this F in this box, and you can say how many particles there are on average. So then this density is transported by the potential, and this expression looks complicated, but it's just this. It's the transport along this, so the time derivative of F is a transport of F along these classical trajectories. And then as an approximation for this exact potential that is different for each particle, you take what they call a mean field approximation. And it's just to say that the potential will be generated by all the particles on average. So you integrate this density over the momenta variables. You have some density that depends on time and space. And then you look at the Coulomb potential that is generated by this density. So then you have a gravitational potential with this sign. If you change a sign, you can also do the repulsive case. This is useful if you want to model a plasma where all the particles have electrical charge of the same sign and they repel each other. But in this talk, we will study the gravitational case. So these are two equations, and they're nonlinear because they're coupled through this this potential. And the sign of the potential is such that you can have, we assume that the galaxies exist, so you can have states where the particles trap themselves by their mutual gravitational interaction. So these are the states that we are interested in. Okay, and this expression makes sense in any dimension, but will be mostly in dimension 3. There are associated to this classical system, you have conserved quantities. and this will be preserved by this flow that is on the first slide. So you have the energy for each point in this phase space. You associate the quantity p squared half plus v plus vf of x. So kinetic energy plus potential energy, and this will be conserved along this transport, and also the angular momentum, which is just the angular momentum from classical mechanics, is also conserved. So one ansatz that you can use if you want to see, okay, are there steady states? Are there states that maintain themselves stable by this gravitational attraction? Then you can look for solutions that are independent of time. E by itself is not a very nice quantity because it's unbounded and so on, or it is not positive definite. But if you fix any cutoff energy E0, and then you can construct a function, a non-negative function, by taking the positive part of E0 minus E to the power k. And this will be, so you assuming the potential looks something like this. So I take the convention that the potential will be a subharmonic function by the expression that was there. The potential is like this. So here it's equal to E0. This is modulus of x. And then you define these f's that are something like this. So you have E0, it sits here. So you have something like this. And depending on this exponent k, here you will go to 0 in a different in a regular way or in a Hölder continuous way, depending on if this k is larger than 1 or smaller than 1. Anyway, if you take this ansatz, this is a bit circular, what I told you, because the potential, the v, it depends on f. So you can propose this ansatz, and then you have to check that you can find the potential v that allows you to close things. But if you do this, and you notice you scale out some things in some integrals and so on, you notice that actually you will have to solve a very classical elliptic equation to find the solution for this. For the potential up to taking E0 minus V will satisfy this equation in the ball where F is supported. And then you can notice that you have a unique solution up to scaling for all sufficiently small exponent scale. So this equation has a lot of steady states, because at each time we take an exponent k, we can have a different elliptic equation, and while this exponent k is not doing any wild things, we can have different steady states. We have many of them. And actually, we can do even more general. We don't have to take a power law. We can take any function phi of one real variable that is compactly supported in negative energies. And then you can find criteria such that this F has compact support, turns out to have compact support, and find a total mass, which would be the total L1 integral. So you have many, many steady states. The problem in this equation is that you have too many steady states. And then once you have a steady state, so you have something that does not change with that over time, you will ask, okay, is this physically relevant? Are these steady states stable? And there is a criterion that goes back to the work of Antonov, that if this function phi that you put here is strictly decreasing, then such as here in this brown, then you have this neutral stability. So that means Antonov's criterion says that for the linear equation, the linearized equation, solutions that start close to some steady state stay close to the steady state at a linearized level. And then there are a series of works that prove this mathematically for the nonlinear equation by Raphael and co-authors. So this is more or less the status. So I've talked about the linearized equation. Let's have a look at how it is. It's not so hard to linearize the equation because the nonlinearity is only like quadratic. So you take a steady state f0, it will be fixed throughout the talk, and expands. In some moment of the talk, p is changed to v. So these are the velocities. And then to write a little bit less things, so this part of the equation that was this transport in this potential well, that is what is denoted by this calligraphic L for the Liouville operator. So this is just the transport along the trajectories. And then if you expand the equation, you will get, and use that F0 solves the equation as a steady state, you will get this kind of equation for V. So you have the transport L in the potential U0 from the steady state. And then you will have an extra term that says how this perturbation perturbs the potential of the steady state. First side, it's like a first order equation, so it's a bit strange. It's not going to oscillate, it's going to either explode or not. But there is to write it as a second order equation, or you see it as a first order, but a system for the positive part, the even part and the odd part separately. Now, even and odd in this context are with respect to the v variable. So you have a function of x and v, and for each fixed x, you project on you define f plus minus dx v is dx v plus minus f. And this makes things nice because L maps even to odd and so on. So you can rewrite it as a single second order equation for the odd part, which has a very nice structure. So you have this Liouville operator squared, and then you have something that looks maybe not so nice, but you can change functions to a function that involves the steady state phi, and you can bring it into this last expression that's over there. So the last expression is a second order equation in time. You have the Liouville operator squared, and then you have something that involves V subscript something is the potential the Coulomb potential generated by something. So this term that is like the reaction term, or that's extra term, and you can write it. You can factor out this Liouville operator and write it as k sub phi, where k is very nice because it has this kernel, which involves the phi. Phi was a steady state. F0 phi composed with e. So this is a function that is as nice as the singularity over here. And then you have a function of the energy, and then you have the Coulomb potential in between. The I put a complex I with the Liouville operator because Liouville is like a derivative. So if we put an I with it, we have something that is symmetric. So you can make sense of this as an unbounded operator in L2. And actually, when we were writing this equation, we had it for the odd part in V. So actually, it makes sense. We're only interested in the spectrum of this equation for functions that are odd in the variable V. So what this linearized operator is doing is all encoded in the spectrum of this operator, because we had something that's like dt squared squared of h equals minus a. See? Yes. It's a circle is a composition here. Phi is a function in real phi is a function in real variable, and you compose it with e. That's a function of phase space. See? So depending on this phi, you have the kernel and actually Antonov stability criterion guarantees, it's not so obvious, but it guarantees that this k phi is smaller than 1, such that the whole operator A is positive definite, such that here you have minus A. So if you think about it, the solutions will be like sine and cosine, more or less. What you can also see is that this k phi is bounded, but it's also compact. It's very nice. So that's the main part of the operator is this first term. The most singular part of the operator is this term where you have minus L squared or IL squared. So it's important to look at the spectrum L, and it's actually very interesting. L is just classical mechanics. So to define L, we fix the steady state, we fix this potential, and we study the trajectories of one particle that is moving in this potential well. And then what you can see is, if you do this kind of drawings in classical mechanics, what you do is you draw drawing. So here you have the radial variable r and the velocity p of. At each time you fix angular momentum, it turns out that you get some effective potential that looks like this, that diverges when you go some angular momentum different from 0. This is E plus. And then, okay, if you're below E0, you will have bounded trajectories in the radial variable that go between these 2 points. So each time you fix an energy, you will have trajectories that oscillate here. If you make a drawing of phase space, they will look like this. So here they have 0 velocity. Here they have positive velocity, so they increase r, and here they have negative velocity, so they decrease r. So you have these kind of shapes. And then, so just one particle is going to make this periodic movement with a certain angular frequency. But as you vary the energy, you will have different of these angular frequencies, unless your potential happens to be exactly an harmonic oscillator or something very special. But if this is not happening, if your potential is not very special, the frequency of this movement is going to depend on the energy and also on the momentum in this higher dimensional case. So what this does is very, very nice to look at, and very actually easy. This simulation is not for the potential that comes from something gravitational. It's just if you take x squared as potential and then you add a quartic term that perturbs it a little bit, you get something like this. So you take an initial condition that's instead of one particle. So you look at a smooth, like a Gaussian centered somewhere. And if you run time, different points will be on different trajectories that goes with different angular speed. So you will, so this picture corresponds to this picture here. So you have an initial condition here, it gets transported, and since some particles go faster and some go slower, it gets stretched out as some kind of spiral, which happens when you mix, I don't know, jam and yogurt or something like that. This is what's called phase space mixing. So it's a phenomenon where something looks like it's converging, because if you can imagine where this goes, if you continue and continue, this filament will get thinner and thinner and cover more or less uniformly a whole region of this thing. But on the other hand, if you look at it as a function, like it becomes more and more singular because it oscillates very strongly. If this one was a nice Gaussian with some Lipschitz thing, this one has a lot of more oscillations. It has more and more oscillations, but if you average it over something small, then it will converge to something uniform. Because it becomes uniform, but not by like dispersing. It becomes uniform by stretching itself out and covering more and more. Yes? So this is the phenomenon that happens if your dynamics is given by this operator L. The way to make it formal is to write this dynamics not in the coordinates r and v, or r and pr, or whatever, but in coordinates that are adapted to this classical mechanics problem that are called action angle variables. And in these variables, you have one that's actually a variable, that's the theta. It's more or less parametrizing where I am on this circle. So this is exactly the angle, because it's parametrized in a way that this increases at a constant rate. But more or less, theta tells you where you are on the circle, and then E and L, energy and angular momentum, tell you which circle we're talking about. Okay, so you can make this change of variables, and you can find these angular frequencies omega. And if you do this change of variables, you see that's what we had there. Well, the operator L is unitarily equivalent to some radial frequencies times a derivative in the theta direction.
To one angle, therefore corresponds different lines. Which is the variable for one angle theta, we have different.
So these are different times. This is initial condition at different. The first is the initial condition, and then you evolve for different times. So it's actually interesting to see that even though this is very, very old classical mechanics, proving properties of this omega beyond that it's locally well behaved and so on is very hard. For instance, to prove that this omega is monotonic with the energy is an open question. And it would help, it's relevant for what we're trying to do here. So trying to advertise this, but it's really not easy, I think, or you have to come up with some very different idea for it. See? That omega is, I'm trying to picture the graph in my head. I don't remember, but it's not so important for. The important property that we need is that the. Okay. In the minus sense, so decreasing. That omega is decreasing in the energy. The important property is that it reaches its minimum at the boundary of the support, which is the boundary of the support is E0. It's the highest energy. But we'll see in a minute. So one very famous result in this context is the paper by Moreau and Villani, and then there are later works that simplify the proof and generalize the methods too, where they study exactly the Vlasov-Poisson model, but for the plasma case, so with the repulsion, and in a kind of idealized setting where you are on the torus. So you're not like going around in physical space, but you're just periodic. And I say just periodic, but it's very hard. There's a lot of heavy machinery involved in this work. So, oh, this is twice. So if we have this omega of E and L, Then we can know everything about the spectrum of minus L squared because it was just derivative with theta multiplied by this. So derivative by theta, you can take a Fourier series and then it becomes just multiplication by integers or 2 pi times the integers. And so the spectrum of this L will be, okay, I will write. So IL is multiplied something that does not depend on. And theta lives on a circle. So if you parameterize the function of theta as e to the k theta ck, if you parameterize a function like this, then you will get out multiplication by k. And then this multiplication by something that depends on E and L. So for each, the simplest value is k equal to 0, then you multiply omega by 0 and you will get 0 in the spectrum. But then if you go to k equal, you will get all possible values of omega and E and L, all allowed values of omega, all values of omega for E and L that are in the support of your function. So you will get something like this. Omega mean to omega. And then if you vary k, you will get twice this interval and 3 times this interval and so on. So depending on how omega min and omega max are, the other ones will overlap or there will be further gaps, but that's not so important. The important thing is that 0 is always in the kernel of the operator, in the spectrum of the operator. And then you will have a gap until the minimum frequency omega. So that's how this looks like. Yes, omega minimum would be. So you have always a gap, or you always have a gap if your E0 is strictly negative, because omega equals 0 would be the period of revolution be infinity. So if your support is period infinities are things that go like this and don't come back. So all of the polytropes, all of the nice examples, they don't have this phenomenon, and you have a gap here. Yes. But so this is a gap for the main part of the operator, and then it has a second term, this case of phi term that perturbs this operator. Okay. So this whole operator A, I'll write this down as well. A is IL 1. Okay, so this first term gives this one, and then the second term is relatively compact because this k phi is like integrating against a very nice kernel. The second part is relatively compact. That means that it cannot move, it cannot change this part of the spectrum, this part of the essential spectrum. But it could create eigenvalues. I wrote also 1 minus k phi because k phi is positive definite. So you can imagine that there might be some eigenvalues that appear here. And this is actually interesting because this part of the spectrum corresponds to this mixing phenomenon, that things get homogenized in some sense. If you have an eigenvalue here for this equation, this eigenfunction corresponds to a mode that just oscillates forever, like the wobbling kink or like wobbling soliton or wobbling whatever. So this is wobbling galaxy. And so one tool to study if these eigenvalues appear is to write the Biermann-Schwinger operator. So now I don't have time to say why it works, but this is the way you write the Berman-Schwinger operator. You have an operator that depends on a parameter lambda, a compact operator, or at least a bounded operator. And it has eigenvalues. And the point is that as soon as 1 is an eigenvalue of k lambda, lambda is an eigenvalue of this operator A. So this gives a very useful tool to study the spectrum of this unbounded operator A by studying a bounded operator k lambda, and it's not at all specific to this Vlasov-Poisson problem. You can use it. It has been introduced first for Schrödinger operators, and you can use it in a huge variety of contexts. So once you have this kind of operator, you can start really working, and then it becomes not so completely exactly beautifully nice, but still you can say very precise and quantitative things. You can say that so in order that they don't seem completely ugly, the results, I defined an auxiliary quantity which has this phi prime, so it's may diverge if you're here, and it has at the denominator something that depends on the frequencies, that depend in turn on the energies, minus this minimum frequency, which is omega star. So depending on how phi prime might diverge when I reach the bottom, the boundary of the support, and depending on how omega reaches its minimum value, how degenerate it is at the minimum value, this rho star is exploding or not. And then you can have two cases. Either, we're not completely in two cases, but we can say if it's very nice in the sense that it's integrable even when you multiply it by x minus 1.
The function that depends on v.
Everything, because everything depends. I didn't want to write something ugly. So everything depends on E, and E depends on V. Everything depends on L. Omega depends even on L, and everything depends on V. So you, but in a complicated fashion. So, but you integrate all of it, and you get a function of X. So if this function is integrable, then you can use this Berman-Schwinger operator to bound the number of eigenvalues. If it's not integrable, then you always have eigenvalues, even if you make, in some sense, your steady state very small or something like that. So not integrable corresponds to cases where this minimum of omega is not at the boundary of the support, which we think that do not exist, but we don't know. Or in cases where this phi prime is exploding too fast at the boundary of the support. So that's the main result that we could do, but it's kind of frustrating because there's still lots of open questions around this. But I think the main message is that this Berman-Schwinger operator gives you like a tool to approach a spectrum of this operator. There are many open questions on. One thing is this essential spectrum. So this essential spectrum comes with this mixing property. It comes with some decay in some sense that you can quantify and so on. So one thing we would like to know is how different dynamics that A generates if I omit the possible eigenvalues, if I don't look at eigenvalues that might be over here. And if I do that, I'm thinking of results that say that this essential spectrum that was absolutely continuous, because it was this multiplication by omega of E and L, and this was a continuous function, that this property is preserved when we add this perturbation term K phi. So this is one question, and there are many tools to approach this for Schrödinger operators, and I don't know really how to approach this when you have this kind of general thing which is kind of mixed and so on. One thing is to get better really bounds on the eigenvalues and so on. And another thing that we were not able to do is to study the flat case. So the flat case is like some idealization of a galaxy that lives in the plane. So you are in two space dimensions, but you still put the gravitational potential for dimension 3. So this is more singular than the original three-dimensional case, because you have a 1 over modulus of x, but in dimension 2. So it's harder. And also because the Coulomb potential comes with dimension 3, it has very nice properties, especially in spherical symmetry and so on, that you don't have even if you restrict to radial things in dimension. And then I think the biggest question is, like, for the nonlinear dynamics, there is a very exhaustive thesis by Christopher Straub that you can find online. And he has done a lot of numerical work that shows for the linearized equation and for the complete nonlinear evolution, and shows that they're very similar, which is different as this wobbling kings and things like that. It suggests that also at a nonlinear level, this oscillating galaxy exists. So that solutions close to the steady state do not converge, even if we admit some weak damping-like sense of convergence to the steady state, but they continue to oscillate forever, depending on the value of k that's hidden here in the function phi. And also one other question is, okay, one question is, okay, we fix a steady state, what happens close to it? Another question is, can we construct maybe maybe not close to some steady state, but can we construct explicit solutions that are time periodic? The answer is yes. Since a long time, there is a model called the Kurtz model, but it has the wrong dependence on the energy. It goes, Antonov's criterion said it was decreasing in energy. This one is increasing in energy. But it is exactly a sphere of constant density if you integrate over the velocity variable that breathes. That is periodic in time. So I think these are all very interesting questions. Thank you very much for the opportunity to speak here, and be happy to.
Thank you so much, Hanne, for the very nice talk, and open the session question. Any someone?
You might have gaps between the bands of in the continuous spectrum.
Yes, it can happen.
Is it possible that you have eigenvalues in those gaps?
Yes, it's possible. It's like typically one expects that this lowest eigenvalue has some would be dominant in some cases, but it's possible. And also, I think because it depends on this omega, these frequencies, and so it's easy to write out what is the conditional omega min and omega max to have a gap here, but it's not easy to, if you have a polytropic solution to the linear equation, to know these values. It's not, but numerically it appears to be in most cases it appears to be closed, this gap. So I think that's why nobody has tried to prove or disprove, because apparently most of the time this gap is not there. But in principle, it could be there if you restrict to a very small support in energy.
It depends on the choice of the function phi.
Yes. Yeah. Everything depends on phi, and this one can be.
Another question?
I just have a question about the literature. Yeah, the Kurtz solution, is well known since many years.
Yeah.
But I haven't seen in the literature a sort of relationship between, for instance, the big number of conserved quantities of the model and a sort of integrability. You know that the breeder is associated to a sort of integrability.
I mean, the model is integrable in this the one thing I know is that motion in 3D central potential is integrable. But then the Kurtz solution is very peculiar because it has constant density. So in that sense, you can construct it explicitly because of this property. But yeah, I don't know what I mean. It has too many conserved quantities because of the Liouville theorem. So you all the level sets of how do you say this? Yeah, all the level sets of F are transported. So the measure of all the level sets is conserved quantity, or any function of E or of F is a conserved quantity. But where this conserved quantities should give the breeder solutions or something like that, I don't know if anyone has looked at it in that way.
The people in Zoom have any question? A curiosity, what is the most difference in the approach that in the application of the flat case that you mentioned in the finished part? What is the most difference in results of the approach?
Okay, yeah. So the result I show you, the only theorem I showed like in a box and so on, that one does not it has an upper bound and a lower bound, right? So yeah, and actually this one probably you can do it also in the flat case, but you have to be very careful to construct everything and so on. This one relies on some bounds. There is something very nice about Coulomb potential in section 3. If you have a spherical if you have a spherical symmetric distribution, then the force at each point is the same as if you would have all the mass concentrated in the center. It's called Newton's theorem, so it's something very old, but it simplifies enormously the calculations that we have to do for the case d equal 3. And that one does not work in d equal 2. But there are also many other things like even uniqueness and uniqueness of a solution for a fixed mass and global well-posedness and many other things that do not work in dimension 2 either. So, but for our specific results, it's more like something that I feel technical because you don't have such a nice property of the Coulomb potential. It's something like minimum, something like that. And this simplifies the computation. Sure. Okay.
Thank you.
Thank you.
Okay, if you don't have more questions, give me thank you again to the Professor Hanne. See you at the next seminar.
No.
Yo traje uno como tercer.
Sí.